The transition from the high Andes to the Amazon basin involves an abrupt drop from 4,000-meter peaks down into dense tropical canopy. Nestled within this descent is the Quince-Mil hotspot. Here, rainfall reaches an extreme 7,000 millimeters per year. Standard climate models divide the Earth into grid squares spanning 50 to 200 kilometers. At that scale, a steep valley like Quince-Mil mathematically disappears. Because these coarse models cannot detect the microtopography, they severely miscalculate near-surface temperatures and wind directions that physically generate precipitation. To prevent these errors from rendering local flood forecasts useless, hydrologists must build entirely new 1-kilometer resolution datasets from the ground up. To understand how topography manufactures rain, physicists use the Weather Research and Forecasting Model, tightening grid spacing down to 5 kilometers. This resolution isolates specific geographic engines. The lowlands of the Fitzgerald Arch actively channel nocturnal moisture fluxes directly toward the hotspot. When researchers mathematically removed the Comacea mountain from the simulation, hotspot precipitation dropped by 40%. A 50-kilometer global grid performs this exact removal by default. It averages out the peaks, presenting a flat, featureless surface to the simulated atmosphere. This reveals a strict physical limit in climatology. If your spatial resolution cannot resolve the mountain, your model cannot predict the rain it manufactures. Solving this requires building a serially complete, high-resolution dataset across an entire national territory, a massive engineering challenge. The baseline instrument for measuring rainfall is the in situ automatic weather station, or rain gauge. But across the rugged, inaccessible terrain of the Andes, these stations are highly sparse. A single broken gauge creates massive blind spots in the regional data. The alternative is to look from above. Satellite platforms provide continuous spatial coverage using infrared and microwave sensors. However, these satellites estimate precipitation by reading cloud top temperatures. Over complex orography, these estimates are highly inaccurate at determining absolute rain volume on the ground. To bridge this gap, engineers deploy a geostatistical interpolation algorithm. It maps the blurry satellite coverage against the precise, localized data of the gauge network. The algorithm uses the physical gauge measurements to calibrate satellite readings, anchoring the estimated heat map to ground reality. This multimodal fusion process produces the PISCOp H dataset. It locks in a 1-kilometer spatial grid, giving researchers the resolution required to actually see the Andes. But a precise spatial grid fails if its temporal resolution remains locked to a 24-hour cycle. Many standard models suffer from a diurnal cycle bias. They systematically miscalculate the exact hours of the day when precipitation peaks occur. This bias destroys predictions for small hydrological catchments, under 500 square kilometers, which respond to intense, short bursts of rain rather than daily averages. This 2D hydrograph plots streamflow. The smooth curve is observed runoff. The jagged, uncorrected line mistimes the daily peak. To fix this, researchers apply quantile delta mapping. This mathematical correction forces the simulated data to align with the observed curve, preserving extreme anomalies. Correcting sub-daily temporal resolution is a strict requirement. Without it, simulated streamflows in small catchments are mathematically detached from reality, invalidating any downstream hydrological impact studies. The utility of this hourly precision becomes clear when we move from the Amazon down to the arid, steep basins of the Pacific coast. These dry environments face a specific threat: highly destructive mudflows triggered by short, intense, and hyper-localized rainfall. When these coastal basins activate, sudden torrents of mud and debris destroy infrastructure and threaten human life. Historically, developing early warning systems here was impossible. The extreme scarcity of rain gauges in these remote zones meant researchers couldn't measure the specific conditions that triggered a collapse. By applying the new gridded hourly dataset, hydrologists can now run high-resolution simulations backward over historical mudflow events to isolate the trigger conditions. This backtesting revealed a precise empirical threshold. The mudflows initiate when rainfall hits an intensity of 1.13 millimeters per hour and sustains that rate for 5 hours. Isolating a precise figure like 1.13 millimeters per hour proves the absolute necessity of hourly gridded data. You cannot engineer infrastructure defenses against flash events using daily averages. The development of datasets like PISCOp and SC-PREC represents a leap from coarse, blind estimation to 0.1 degree hourly precision. These grids mathematically reconstruct atmospheric physics and topography, replacing smoothed statistical averages with high-fidelity modeling. In regions like the Amazon, where intense droughts and floods are increasing in frequency, relying on low-resolution models masks the severity of the threat. Reliable early warning systems for these events are entirely dependent on the continuous algorithmic fusion of physical gauge data and satellite telemetry. Preparation for environmental shifts depends entirely on the granularity of the data we collect. Our ability to model, predict, and ultimately survive future extreme climate events is absolutely bounded by the spatial and temporal resolution of our data.